Hi everyone, welcome to my Lewis structure lecture. We're going to be looking at how we can draw the Lewis structure. They're going to be a little bit about a formal charge calculation, and then I'm going to show you a couple of practice. Okay, cool. Okay, so there are a lot of molecules around us that are covalently bonded, right? So these are all our, molecular compounds, and we should be able to draw them on papers, right? This is just a two-dimensional. And that's why we have a series of steps here. I'm going to present them all. I'm going to walk you through that, which is going to be our Lewis structure drawing. Okay. The first step is determining the total number of valence electrons. And that means you need to look at your periodic table, whatever is the group number, right? That is going to give us the valence electrons. So it is going to be from 1 to 7 typically. You may have the noble gases, but they are a lot less common, right? So you're going to add them all, and that will be the source of our electrons, okay? Now, if you have an ion, let's say you have a cation or anion, you also need to consider that, right? So you would consider an extra electron if you have a negative charge, and if you have positive charge, you just need to remove electrons, okay? So when you're done with that step, the next one is going to be arranging the atoms in a way that you have your least electronegative atom in a center. Now, this wouldn't be happening for hydrogen because hydrogen can never have more than one bond, right? Also, if you have a halogen, right, they're going to be typically on a terminal, so they're not going to be on the center because they cannot have more than one bond, mostly, right? This is like what we see typically for halogens. Then we're going to go ahead with the step number 3, which is connecting the atoms with single bonds. When you draw a single bond, that means you have used 2 electrons, right? One pair of electron, which is presenting the shared electron between the center and whatever that atom is. You need to subtract that from your total number of electrons, right? Then you go ahead with your lone pairs and you try to distribute them so that you are reaching to 8 electrons, and you would add them to all the elements surrounding your center. So all the outer atoms are going to catch the electrons first. Then you subtract them from the total number of electrons, right? And if you have any left over, then you would add them on the center. Okay, so by this time, all of the electrons have been used. Okay, looking at the next page. Then we're going to go ahead and check in the octet rule. We want to make sure that the atoms are all having 8 electrons, right, following the octet. Now we know that there are a few exceptions, right? The most common exception is for hydrogen, where we know that hydrogen cannot have more than 2 electrons. So you can say this is the duet, not an octet. Also for boron and aluminum, they're going to have less than 8 electrons typically. They have 3 bonds, which is 6 electrons. You could potentially have an expanded octet, which means that more than 8 electrons, and that happens possibly for the elements in period 3 or anything beyond that. Maybe for phosphorus, maybe for xenon, right? Then you would use multiple bonds if you need it. This means that if you're missing any octet, right, in order to satisfy the octet, you try to borrow electrons and make double bond or maybe triple bond as you need. You may possibly have some resonance structures as well, which is the cases that I have equivalent positions for my double bond. Okay, I'm going to show you all of that in our examples. Before that, I have one more slide for you. And that is about the formal charges, right? So this is going to be step number 7. It's optional, but it's highly recommended, right? So in order to calculate the formal charge, you can go by valence minus sticks minus dots. That's so easy to remember. Okay, now the idea here is if you don't have any formal charges, that's the best. That's like the ideal structure. But if you have formal charges, you try to, keep them as small as possible. This goes for the cases that you have multiple resonance structures and you try to pick the best one. Also, keep that in mind if you have a negative charge, it's better to place that on more electronegative atom because they can stabilize that. And if you have positive charges, we try, right, to place them on less electronegative atoms. Okay, so these are going to be our steps. Done with that. Now we're going to be looking at our practice, starting by the first one on the next page. Okay, so here is our first practice. Draw the Lewis structure for phosphorus trichloride. Okay, so I'm going to start by very first step, which is counting our valence electrons. For phosphorus, I'm going to have 5 electrons. For each chlorine, I'm going to have 7, and I have 3 of them, so that should be 3 by 7. And that would give me 26, right? VE stands for valence electrons, okay? I don't have any charges, so we're okay with that. Then I'm going to go ahead and put phosphorus in the center because it has less electronegativity than chlorine. And I'm going to have the chlorine around it. Using single bonds, right? I have 3 of them. There you go. So because I made 3 bonds, I have used 6 electrons. So that should be -6. And that means at the moment I have 20 valence electrons. This is my remaining electrons. Okay, then I need to go ahead and add these electrons as lone pairs, starting by chlorine. And I'm going to have 3 pairs here to satisfy the octet, right? So I have closed shell for chlorine here, here, and here. And that means I have used 18 electrons to make all of these lone pairs. So I'm going to say 20 minus 18, and I still have 2 valence electrons remaining. Then I'm going to go ahead and put them on phosphorus, right? And that means I don't have any more electrons. We're done with that, right? So once you get rid of all of the electrons, once you use all of them, right, then you go ahead with your octet. So everybody is happy. I have 8 electrons for everybody, right? That will be perfect. I don't need to make any double bond. I don't have any resonance, and that's it. We're done, right? Now, let me show you the formal charge for, let's say, chlorine here. It's going to be valence. I have 7 valence electrons, minus sticks. There's only 1 stick, minus dots, and I have 6 of them. Right? So that means I don't have any formal charge for chlorine, and I love it. That's perfect. Do the same thing for phosphorus, right? So for phosphorus, I have 5 valence electron. And then for the sticks, there are 3 of them. Dots, I have 2 of them. That means, again, I don't have any formal charges for my phosphorus. So this will be the perfect structure for my PCl3. Cool, cool. Looking at the next one. So this one is for nitrite ion, NO2, and I also have a negative charge. So I know that for my nitrogen, I have 5 electrons, right? Valence electrons. I have 2 oxygen, so that will be 2 by 6. I also have a negative charge, so I need to add that here, and that would give me 18 valence electrons. Then I'm going to go ahead and place nitrogen in the center because it has less electronegativity than oxygen. And I'm going to have my oxygen on either sides, something like this. I have made 2 bonds, so I need to go -4, right? And that means at the moment I still have 14 valence electrons. I'm going to start placing them as lone pairs, starting by the oxygens. And I have used 12 electrons. That means I still have 2 valence electrons, and I'm going to place that on my nitrogen, right? And that means I have used all of my electrons. I don't have any more. We're done with that, right? Now, looking at your structure, is that the best or can we do better? Yeah, I haven't checked the octet. The next step is checking the octet. And as you can see, your nitrogen has only 6 electrons. So I can borrow electrons either from the left oxygen or from the right oxygen, right, to make a double bond. And that will be here. So either I have N double bonded with the left oxygen or double bonded with the right oxygen, right? They are equivalent. They are exactly the same. So I'm going to have 50% double bonded with the left one, 50% with the right one. And we are using double-headed arrow to present the resonance. You can place all of your pairs of electrons to make sure that everybody is cool now. We have octet for all of them, right? Bear with me. This is not easy. Okay. There you go. Perfect. Okay. Then I'm going to look at my formal charges. Okay. So let's do that for this oxygen double bonded, which is going to be 6 minus 2 minus 4. So that's 0. I don't have any formal charge here. But if you do that for the oxygen with a single bond, that will be 6 minus 1 minus 6. So I have a negative 1 formal charge, right? So here's the idea. I know that I have resonance. So there are going to be two forms existing in my equilibrium, in my solution. I'm going to go by the combination of these two, which is going to be known as your resonance hydride. We'll talk about these in a lot more details, but for now, I'm just going to call this my resonance hydride. Now I have just partial negative charge on each of these oxygens, right? I don't have a full negative charge. So that's the whole idea. We'll try to, reduce the charges to make the molecule more stable. We typically use this square bracket around the molecule to present the overall charge, right, which is -1. And don't worry if you are not 100% sure about the story of these structures here. They're going to be definitely a lecture for that. Okay, stay tuned for that. Cool, cool. Thank you, thank you. Okay, if you like this video, please go ahead and give it a thumbs up. There are going to be more coming up soon. Take care, enjoy the rest of your day, and bye-bye for now.